h is square root of Zn. So what should be the value of the h value?
Square root of h Zn.
And assume that h is square root, obviously 1 over n. So this is going to be 1 over square root of n, okay, times z.
Z1.
Zn, but z capital. Okay. Or you can say this would be 1 over square root of n, where I goes from 1 to n. L, where Li's are your,
Scaled ones.
not scaled, okay? They're not scaled one. Please minute. Just write explicitly. So if I say I have this nh, which is n by n, okay, and I'm keeping it to 1 actually. Okay? So what does it mean? So just keep n, so this means that take n to be equal to capital N. So if you're going to take n to be equal to capital N, h is 1 over n, so it's going to be 1 over square root of n, and Zn is going to be Z capital N actually, so you can have it. Okay. I like to write the usual theorem, which is a simple consequence of a central limit theorem. So I would like to know what. So at the moment we talked about, okay, its increment, for a scale random walk, for example, its increment are going to be, independent, expectation would be 0, the variance would be the, difference of times, okay, and martingale-ness and all that. Okay. So we haven't yet talked about the distribution of the Zn actually. The distribution of Zn. Okay. Can you roughly predict what should be the distribution of Zn? The gains that you have. And hence you can also predict the distribution of the scale, gains. So Zn is the sum of IIDs. Okay, each one of them has expectation 0 and variance 1.
Central limit theorem.
Okay. So you have the central limit theorem, which tells you that it converges to in distribution to
normal distribution.
normal standard normal distribution. Okay. And the same would be the case here. That if you take a scale random walk, okay, and you see it after the n instant, it would converge to the standard normal distribution. Okay. So I'm just writing, by central limit theorem, okay, what you can prove is that this is scaled random walk, for example. Even it's not necessarily about n. You can take any instant. This would be still true because ZH is written in the terms of Zn. Okay, you have to scale h appropriately. Okay, and I know that Zn is the sum of IIDs. Okay, then square root of h Zn is also sum of IIDs, but the means are different. So in case of simple random walk, they were 1 and 0. Expectation was 1 and variance was 0. But here you have what expectation is, what would be the expectation? 0, but the variance is h actually. Okay, the standard deviation is h. That's what the key difference is. Okay, and I know that if you have IIDs, okay, with whatever mean and whatever variance you have, you take their sums, the sum would always converge to the normal distribution actually. Standard normal when if you subtract the mean and divide by a standard deviation. Yes. If you want ZH and H to converge to standard normal, then you need to do what?
Divide by
You need to subtract the mean and divide by square root of h actually. Square root of h, which is the standard deviation.
yes.
Okay? And that will converge to the CLT. In other words, ZH1 would converge to, is going to be normally distributed with mean 0 and 1. Okay? And you can also prove that ZH and H would converge to, but converge in what sense? Converge in distribution. Okay? Converge in distribution to what?
And OH.
N,
Oh.
0 and H actually, this is going to be there. Okay? So do you remember what is meaning of convergence in distribution precisely?
Measure probability measure.
Convergence in distribution. So this means that the distribution function of this random variable, okay, will converge, as a sequence of real numbers to the distribution function of the standard number random variable actually. Okay? So now you can check the precise definition as well. That's the case. So conclusion before moving ahead. Finally, if I have a random walk, it has what key properties? It starts from 0. It has independent increments. Its variance, okay, so its expectation is 0, variance is 1, and it converges in distribution to the, or it has a distribution in long run that is normal distribution, standard normal. How about a scaled random walk? The same, starts from 0. Increments are independent. It has distribution roughly when n goes to infinity or h goes to 0. Okay, then this is going to converge to what? Converge to normal distribution. Okay, with expectation 0 and variance h. And in addition, a scaled random walk has a good properties that it's a continuous process as well. So its trajectories are continuous actually, which was not in, for example, in simple random walk. Simple random walk is just collection of the dots actually. While the scaled random walk, the way we have defined it, is a continuous process actually. So these 4 properties. And let me throw the definition precisely of what you call the Brownian motion actually. Okay? So these are the precisely properties that any process that have, we're going to call it a Brownian motion. Okay? So what's the definition of a Brownian motion? So I'm writing a, okay, some people like to also call it a Wiener process. Okay. Wiener process. And I would like to write a precise definition of it. So, Brownian motion is a map, okay, W from 0 to infinity to omega into r. Okay. So it's a process which depends on time and has some randomness associated with it because omega is a sample space and throws the values into the r. Okay. Any process, of this form for some omega fp, some probability space, okay, measurable. So it's a map that is measurable with respect to the product sigma field. Okay? Product sigma field. And which is that product sigma
S,
field?
S, tensor.
Borel sigma algebra.
Into tensor.
Okay. And
Yes.
F. Okay. F. And I know that this is a sigma field, you can recall it, that it's a sigma field roughly generated by the rectangles from the Borel sigma algebra and Borel sigma algebra and okay. So it's measurable with respect to the product sigma field. We talked about in our measure theory course in detail what do you mean by product sigma field, we constructed it. So it's a sigma field generated by rectangles of the form B cross A, where the B is a Borel set, okay, and A is an event from
Field.
field actually. Okay, so we know the product sigma field is this, such that so I'm writing a precise definition, okay, not just a engineer's definition, because when engineers write it, they're not interested in that. They just say processes Brownian motion starts from zero, continuous trajectory, then just write it. So Brownian motion is a map that is measurable with respect to the product sigma algebra, okay, and it satisfies these properties. So what are these properties? That it must start from zero, PR most surely, okay. Second, so I know that my scale random walk starts from zero. Second, for two finite instants, the distribution of the increment, okay, the distribution of increment is normal distribution with mean 0 and variance P minus S. Or you can simply say, WT, so if we choose S to be 0, WT is normally distributed with mean 0 and variance T. Okay? We know our scale random walk also has this property. And what? And the third property is that if you take finite number of instants, for example 0 less than or equal to T1 less than or equal to T2 less than or equal to Tm, okay, then all of the increments Wtn minus W Tn plus 1 minus W Tn okay, yes, W Tn are independent. Okay, for all n equal to 0 up to n. Alright? So in other words, if you see the process on T1 to 0 interval and the C process from T2 to T1, the output or the behavior of the process on this increment must be independent of what was it on the previous increment. Okay. And the fourth property is that that each trajectory, okay, over the all times. So this is a map from T to Wt omega. In other words, if you pick a trajectory of the path process and you look at it over the entire times. Okay? So you take a trajectory and look at it for the entire times, you will see that it's always continuous. Okay? There are lots of kinks at every instant, but it's continuous. Okay? In other words, so almost all paths from t to w of t omega are continuous. Okay? Are continuous. And continuous in what sense? In a simple sense, because WTW is a number actually. So we are talking about one-dimensional continuity, limit equal to the value of the function. Okay? So they are continuous. Okay? So, any process that is measurable with respect to the product sigma algebra starts from 0, and on every small increment, I mean if you look at any increment, okay, no matter how small and how big it is, from instant s to t, it's always going to look like a normally distributed random variable. And all increments, so if you take the finite number of increments and see the value of the process on each of that increments, all of the increments are independent of each other actually. Okay? And almost all paths of it are continuous for the entire time actually. W
नहीं सर t की जगह w
ये ओमेगा होगा.
नहीं सॉरी ओमेगा होगा ना t की जगह ओमेगा लीडिंग टू w of t का होगा
T in the time.
path
No. Okay. So I'm saying fix a path omega. So imagine you fix a trajectory. Okay. And you just see its variation with respect to time. Omega
One
is
variable.
fixed, the time is variating. Okay. You will learn how to simulate it actually. So I've said other Shah, you can spare some time and tell you that how to simulate all that. He also told me something interesting. He said, you already know how to simulate, the basic probabilities actually. ये किया हुआ है आपने? या भूल गए होंगे? Once upon a time पढ़ा था. वो कह रहे मैंने तो पढ़ा है कैसे experiment, coin tossing experiments कैसे करने हैं हमने.
Range function use करें.
अच्छा together
Yes. We do.
What I want is that इसमें for example some of the discrete stochastic processes you can simulate them actually, some of things actually, how to simulate them. Anyway, we'll also talk about the simulations of it. So when you're going to simulate, a process, so when you're talking about so if I am fixing, for example, so if there are, for example, 10 omegas in your sample space, that means that it can have 10 possible trajectories. Okay, it's going to have 10 possible trajectories actually. You have 10 possible trajectories. So for each omega, so if you fix omega, in other words, if you take a particular trajectory, then it's always going to be continuous. Okay. What if I am fixing at time t? Fixing time t and looking at omega and variating the omega. So it's like you are fixing a time and you want to look at how all of the these possible trajectories are behaving for every one of them. Okay. Construction, I'll discuss tomorrow construction, not today. But let's talk about some of the elementary properties of the Brownian motion. Okay? What would be the one of the example of it? So we just scale random walk is one example here. Some people would like to see Brownian motion as the limit of the scaled walk. So you have a scaled walk, okay, defined for every h, for fixed h, and then you take h goes to 0. Okay, so when you get h, what do you mean by h goes to 0? So in other words, each interval is being infinitely sliced actually. Okay, because that capital N goes to infinity and h goes to 0. Then the process is what do you call Brownian motion. So the Brownian motion can be seen as a limit of scaled random walk. We know that the scaled random walk has all these properties. So what are some of the intermediate properties of it? Some of the properties. So one of the property is that this, in other words, if you see this process Brownian motion with respect to the time actually for a fixed omega, okay, a function w that takes 0 to infinity, takes values in L to omega. So can I see W as a map from 0 to infinity to L to omega? Why W belongs to L to omega? Why it belongs to L to omega? Would that be a valid thing to say? So it's there in definition.
Sir, of course, all parts of fourth point.
And continuity doesn't tell you. Continuity tells you it's in C of omega. Okay. Maybe something like that. Not C of omega, but
C of 0 to infinity.
0 to infinity, yes. Not C of omega.
I think one of better stuff. Sigma is better.
No, product of sigma.
The main function की आ रही है 0 to infinity वहाँ पर to.
So it's here. Think about it. It's here. So substitute s equal to 0 here. So what is the distribution of WT? It's normally distributed with variance 0 and
Mean 0 and
mean 0 and variance WT. Okay, right? Now what would be the variance of a random variable that has mean 0?
Compute the
Expectation of that square.
Exactly, so the expectation of that is square. So when I am saying that variance of this is t, the expectation of WT square is what?
Is some finite.
Is equal to t, hence finite, so you have it. Okay. Do you see what I'm talking about? So it's here. That since the variance of this is t, the variance is equal to the expectation of WT square. And that is finite, so therefore, so it's a function, so it's a, at least we saw it's well defined. Okay? So this function will be the process is continuous and nowhere differentiable. Okay. It's nowhere differentiable. Okay. It's continuous and nowhere differentiable. That's the first thing. In other words, if you see Brownian motion as a map from 0 to infinity to omega, okay, then it has these two properties. So how can I show the quantity in L to omega? So how can I show it? So what should I do so that I can show W defined continuity. Roughly. So we have it. Limit h goes to 0. W of t plus h must be W of t. But in what sense? L to omega sense. This limit should exist in L to omega sense. Okay? So what would be the meaning of, so how can I verify that?
Expectation of this difference.
Yes. So take the increment, small increment, and take W t plus h minus W of t square. So what is it? Do I need to tell you?
0.
Come on. Go for the definition. It tells you that Wt minus Ws has variance t minus s actually. So this must be
T minus
t plus h minus Tn.
Which would be h.
Okay? And hence this is h, so goes to 0 as h goes to 0. Right? So it's continuous in L to omega sense actually. That's not differential in L to omega sense. Nowhere differentiable. In other words, you can't find an instant t where this function is differentiable. That's what it means. So you have the kinks at all times. Okay? So now give me the definition of differentiability in L to omega. So what should I do? Now you should be able to tell me what should I do so that I can know that it's nowhere differentiable actually. I need to take the differentiability and show that the limit shouldn't exist. But the question is, what should be the definition of derivative roughly here? Because we know that L to omega is a pretty complicated thing. You can have different versions of derivatives actually. Okay? So you need to compute a limit. The way you computed the limit for continuity. So we also know what is the meaning of differentiating a derivative with respect to time. Definition क्या होती है? Derivate की कोई भी function ले f of t
Plus h minus f of
f of t plus h minus f of t divided by h and take limit h goes to 0. But now you have to take that limit in
N2.
So what should I do? Expectation of
Wt plus
W of t plus h
minus W of t
W of t over h
whole square.
and a square entire h square. Okay? And now you will see the culprit actually. So this guy is going to be 1 over h square and this is going to be h. We have this 1 over h actually. This h doesn't go away. Okay? So this is gonna blow up as infinity as there are some exercises, I'm just mentioning those, maybe some of those I would use. You can show, you should be able to show that if you have two instants, S and T, okay, 0, S and T are two instants, 0 to infinity, then the expectation, and this expectation is expectation with respect to what that underlying probability space. Okay, so you are talking about expectation here actually. So the expectation of W of t and W of s is the minimum and t. Okay, that's one exercise that you have to do. And you can also show that it's not just about this expectation, but if you compute the covariance of W of t and W of s, you're still gonna get minimum of s and t.